In this video, we apply the limiting reactant concept to calculating the mass of product produced when we are given the mass quantities of two reactants. Previously, we considered a scenario in which we were given 5.78 grams of butane and asked to find the mass of carbon dioxide produced if the butane underwent complete combustion in the presence of oxygen, as represented by the balanced chemical equation shown here. And what we found was that 17.5 grams of carbon dioxide would be produced. Now, it's important to note that in that scenario, there was an unlimited supply or unlimited amount of oxygen available, and oxygen was said to be present in excess, meaning that butane was, in fact, the limiting reactant. It was the reactant that was completely consumed in the chemical reaction, so the moles, and therefore the mass of carbon dioxide produced, were determined by the starting moles and starting mass of butane. What about we present a new scenario where we are still given 5.78 grams of butane available for combustion, but this time we are only given a limited supply, 15 grams of oxygen. And the question is, again, how many grams or what mass of carbon dioxide would be produced? Now, in this case, both reactants have a limited supply. We've got 5.78 grams of butane and we've got 15 grams of oxygen. One of them is going to run out first. The question is, which one? And it's important that we identify which one is going to run out first, or which one is the limiting reactant, because the moles of product, in this case the moles of carbon dioxide, will always be determined by the starting moles of the limiting reactant. Now, we can look at this 15.0 gram quantity of oxygen and think, well, that's significantly greater than the 5.78 grams of butane, so perhaps oxygen is still the reactant that is present in excess. The problem with that type of thinking is that you cannot look at the mass quantities and determine this directly. We have to determine how many moles of each reactant is present, because it is the number of moles, not the mass, that is required to determine the limiting reactant. You'll recall that in doing these types of stoichiometric calculations, we first have to convert the mass of reactant in step 1 to the moles of reactant, and then we proceed through step 2 and step 3 to calculate the mass of product. However, when we are given the mass quantities for two reactants, as in this case, we are going to have to carry out step 1 twice in order to determine the limiting reactant. And the reason we need to do this is that because in step 2, it is the moles of the limiting reactant that is used in calculating the moles of product produced. And so here is our scenario again. We are being asked to find the mass in grams of carbon dioxide when we are given the mass of both butane and oxygen. And this is actually the key to identifying whether one of these stoichiometric problems is in fact a limiting reactant problem. Because if two or more reactant quantities are given, then you will first need to determine which reactant will be the limiting reactant by carrying out step 1 multiple times, in this case twice, before you can proceed to step 2. So we'll start by carrying out step 1 with butane. Using the molar mass equation, we get moles of butane equals mass of butane divided by the molar mass of butane. We've got the mass of butane as 5.78 grams, that's given in the question, and we calculate the molar mass of butane to be 58.122 grams per mole. Remembering we need to refer to the periodic table to do this calculation of molar mass as a separate calculation. Plugging these numbers into our calculator, we get 0.0994 moles of butane from our 5.78 grams of butane. We can now carry out step 1 for oxygen. The moles of oxygen equals the mass of oxygen divided by the molar mass of oxygen. We've got 15 grams of oxygen, and the molar mass of the O2 molecule, which has 2 oxygen atoms, equals 32.00 grams per mole. Remembering again, we need to refer to the periodic table to do this calculation of molar mass. Plugging these numbers into our calculator, we get 0.469 moles of oxygen from our 15 grams of oxygen. So we have now carried out step 1 twice, and we've got 0.0994 moles of butane and 0.469 moles of oxygen. We can look at this number here and we can see that the moles of oxygen is significantly greater than the moles of butane. And so we might conclude that oxygen is therefore present in excess and that butane is the limiting reactant. Well, in this particular case, we would be wrong. That is not the case. What we have to remember is that the moles of O2 need to be 13 on 2 times the moles of butane. And that 13 on 2 ratio comes from the ratio of the stoichiometric coefficients. The 13 in front of the oxygen and then 2 in front of the butane. So 13 on 2 times the moles of butane actually equals 0.646 moles. And this number here is actually larger than the available amount of moles of oxygen. In other words, there is not enough oxygen present to react with the amount of butane. And so in this case, oxygen will be the limiting reactant. It is the reactant that is going to run out first. There will be unused excess butane left over after the reaction has gone to completion. And it's important that we've identified oxygen as the limiting reactant because the moles of product, the moles of carbon dioxide in this case, are now going to be determined by the starting moles of the limiting reactant, which is the starting moles of O2. Now, if we want a shortcut to determining which reactant is going to be the limiting reactant, we perform step 1 twice as we've done, and we get these mole values here. And what we do then is divide the moles of each substance by its own stoichiometric coefficient. So the moles of butane is divided by its own stoichiometric coefficient, 2, and the moles of oxygen is divided by its own stoichiometric coefficient, which is 13. The values we get when we perform these divisions are 0.0497 and 0.0361 respectively. This number here is the smaller of the two. Whichever value ends up being the smaller, that's the substance that will be the limiting reactant. So again, we find that oxygen is the limiting reactant and the moles of carbon dioxide are therefore going to be determined by the starting moles of oxygen. So in effect, we now ignore the step 1 calculation that we carried out for butane, and we are only interested in the step 1 calculation that we carried out for oxygen. Now that we've carried out step 1 and identified the limiting reactant, we now need to carry out step 2 and then step 3. So in step 2, we calculate the moles of carbon dioxide that are produced using this expression, moles of carbon dioxide equals 8 divided by 13 times the starting moles of oxygen. Remembering it is the starting moles of the limiting reactant oxygen which determine the moles of product produced. The ratio of 8 on 13 comes from the stoichiometric coefficient of the substance we are trying to find information about, in this case carbon dioxide, divided by the stoichiometric coefficient of the substance we have been given information about, in this case oxygen, the limiting reactant. And that ratio, 8 on 13, is multiplied by the starting moles of oxygen, which we just calculated in step 1, and that will be 8 on 13 times 0.469 moles, which equals 0.289 moles. So we now have the moles of carbon dioxide that are produced, 0.289 moles. In step 3, we convert the moles of carbon dioxide to mass of carbon dioxide using the rearranged form of our molar mass equation, giving mass of carbon dioxide equals moles of carbon dioxide times the molar mass of carbon dioxide, which equals the 0.289 moles that we just calculated in step 2 times the molar mass of carbon dioxide, which we can calculate in this little side calculation here to be 1 times the molar mass of carbon plus 2 times the molar mass of oxygen. Remembering we get those values directly from the periodic table, and the molar mass of carbon dioxide being 44.09 grams per mole. We substitute that into the equation and we get the mass of carbon dioxide produced to be 12.7 grams. So in the first scenario for the combustion of butane, we had 5.78 grams of butane present in an excess of oxygen, and we produced 17.5 grams of carbon dioxide. In the subsequent scenario, we again had 5.78 grams of butane, but this time we had a limited supply of oxygen, only 15.0 grams of oxygen available. And in this scenario, we only produced 12.7 grams of carbon dioxide. And that's because the oxygen limited the reaction. The oxygen ran out first, and there was some leftover unreacted butane, and therefore less carbon dioxide was ultimately produced.